So today we're going to talk about areas of rectangles. By the way, we all know how to find the areas of rectangles. What is the formula for the area of a rectangle? Yes?
Length times width.
Length times width. Exactly right. Guess what? That's our theorem today. So we're going to actually prove that, okay? So, but in order to prove it, you're going to need some postulates that we need here. But we're going to talk, before we talk about some of these postulates, somebody read this for us. How about we start with, Yvette, can you read this for us?
In everyday conversation, people often refer to the area of a rectangle when what they really mean is the area of a rectangular region.
Yeah, because rectangle is just four-sided figure, right? If we're talking about area, we mean the right, the area of the rectangular region. So, but it's okay. We could still use that, but just be aware of it, okay? So, and as it says, we will continue to use this. How about, can somebody keep on reading? Esther, over here, can you read this for us?
We will consider this common practice to simplify our discussion. Thus, when we speak of the area of a triangle, we mean the area of the triangular region that includes the triangle.
Yeah, so we will continue to use this, but you don't know what it means, right? All right, now, somebody read this part. How about Young? In chapter 1.
In chapter 1, we accept the postulates that enable us to express the length of segments and the measures of angles as positive numbers. Similarly, the areas of figures are positive numbers with properties given by area postulates.
So the areas of figures are positive numbers, right? The areas are positive, just like length are positive and so forth. All right, so here's our first postulate. This is it. The area of a square is the square of the length of a side. And of course, you know that all the length of the sides of squares are what? Equal. They're all equal, right? Length are equal. So write this down. I'll wait. And this is our first postulate of this chapter. Okay, so if this is 1 unit right here in this picture, and I have this square, what is going to be the area of the square? Just using the postulate, it is 1. Now, do I just say 1?
No.
What should okay? Hold on. What should I say? How about Brandon? What should I say? Instead of 1, I should just say
1 unit.
what 1 unit is this? The one on the left, right? So this, if I'm talking about area, what do we do with the units? We multiply them, right? So this is 1 unit square, right? Does that make sense, guys? So please be careful, right? For the areas, you need to square the unit. They say square unit. If it was centimeters, what would you say? 1 centimeter squared, right?
1 square centimeter.
No, you say centimeter squared. Or if it's meters, you say 1 meter squared, and so forth. Does that make sense? The reason is because you're multiplying, right, these two units together, right? What is centimeters times centimeters?
1 centimeter square.
Centimeter square. Does this make sense? So that's why for the areas, you square the units. Okay? Now, let's think about it backwards. If I told you that the area of a square is 9 square units, what is the length of these? What would be the each of the length of the sides? How about thinking backwards? This Esther over here. What do you think? If the area of the square is 9 unit square, okay, square units, what is the length of the square? 3. Would you not agree? Pretty straightforward, right? That's easy. All right, so let's move on to the other postulate. Okay, here we go. So the postulate next is, oops, before I show it to you, it's called, it's got a name. It's called the area congruence postulate. I bet a lot of you can guess what this postulate is going to say because it's the name kind of gives it away. Anybody want to guess what this might be here? Eric, what do you think? Area congruence postulate. Not quite. So basically, if you have two figures that have the congruent, if the two figures are congruent, what can you tell me about their area? Yeah, they're the same. That's basically what it is. Okay, so it says, if two figures are congruent, then they have the same area. Okay. Yeah, it's pretty obvious because of the name, isn't that right? Okay, so write that down, because we're gonna need these postulates to prove the area of a rectangle. It's length times width. They actually use base and height. Okay, so they're gonna use base and height. Anyway,
So if they're similar
write this down.
on the area-
not similar. They have to be congruent. They have to be congruent. If the two figures, look what it says.
What about if they're similar, are they proportional?
Oh, very good question. We're gonna actually hit that when we get to the. Don't worry about it. But actually, it turns out it's a little bit different than what you might think. The area is not going to be proportional. It'll be something else. Anyway, we'll get there. Okay. So here's our next postulate. It's called area addition postulate. What does this remind you of?
Segment addition.
What else? There's one other one.
Arc.
Arc. Okay, so good. Arc. Okay. Right. So what do you think we mean by area addition postulate? How about Amy? What do you think? Any guess? What do you think it's going to say? It's very similar to segment addition postulate, angle addition postulate, arc addition postulate.
Areas are added.
Yeah, exactly. Basically, that's what he's saying. It says the area of one region is the sum of the areas of its non-overlapping parts. And as you can see, why you need the non-overlapping parts, because if they were overlapping, right, it won't work. Right? Here's a picture. It's basically saying this. If I have like areas like this, right? Take a look at the one on the left. What is this total area? PQRS was the area 1 plus area 2. Right? And area 1 and 2 are not overlapping, right? If they were overlapping, it won't work this way. Same thing for that second example. You have area of ABC, same as area of 1 plus area of 2 plus area of 3. Easy enough? Okay. Pretty straightforward. Okay. So write that down. I'll wait. So write this down. We're going to need some vocabularies like base and things like this. Base and what else? Altitude and height. First of all, they're going to tell you what a base is for a rectangle or a parallelogram. Guess what a base of a rectangle or parallelogram is? What's it say? Josh?
The base is like the bottom part, or like the.
Yeah, that's what we think. But look at what he says. What's the base of a rectangle or parallelogram? Hint, hint.
Sides.
Yeah, any size. Turns out, if you have a rectangle or a parallelogram, any size could be a space. Doesn't matter. It doesn't have to be one on the bottom. You know what I mean? Right? Because you could always rotate them, right? Or you could just, right? It doesn't really matter. I'll show you why. Look at this picture. You see this rectangle down here on the left, right? You could call this the base. This is what we're used to thinking of, right? Base. But this side could be base. Then this side becomes the height and so forth. Right? Look at this parallelogram. This could be the base, or this could be the base. It doesn't matter. Any size of a rectangle or parallelogram could be the base. Is that okay? So that's the definition of the base for a rectangle or parallelogram. All right. So the length of the base, we use a small letter b there. In the text next, okay. So we use base either to refer to either the line segment or its length. Okay. So when we say base, we could be talking about the actual line segment or the actual length. Okay, so we sort of use that interchangeably. What's an altitude of a rectangle or parallelogram? How do you think we're going to define this? Okay, Tony, what do you think?
Well, it's the distance between the line with the opposite of the base and the base, the distance between them.
Yes, and distance between them. How are we going to?
Line
Perpendicular segment is exactly right. So turns out, write this down. Whoops. I don't know why it keeps on. An altitude to the base is any segment perpendicular to the line containing the base from any point on the opposite side. So that's the definition for the altitude. So write that down. An altitude of a base, an altitude to a base is any segment perpendicular to the line containing the base from any point on the opposite side. It's kind of interesting though. Take a look at this one right here. You see this altitude? Right? Look at this altitude. You see, this is if I call this my base, look at my opposite side. If I go from here, go down straight, it doesn't even hit the base. What am I going to do with the base if it doesn't intersect the base? You have to? Yeah, you got to extend it. Okay, sometimes that's necessary. Okay? So, don't think that, the base and the altitude does not intersect. Well, you got to extend the base. Does that make sense? All right, then what's a height? I thought they were the same thing. Height and altitude, aren't they the same thing? Well, what do they tell us what height is? How about Austin? What's it say?
Height is
the distance from the base to the top.
Yes, there you go. They tell us it's the length of the altitude. It's called the height. But you know, we use that interchangeably, right? Length, I mean the height and then the altitude. So it's okay, but if you're being really careful, height is the actual length of the altitude. Does that make sense? Altitude refers to the actual segment, right? And if you're talking about actual length of that altitude, it's called the height. Okay? Does this make sense? All right, so I'll go ahead and write it down. I'll wait for you. Now we're finally ready for our theorem. What did I say the theorem was? The area of the rectangle, right? And we already know what it is. The area of the rectangle is what? Product of its base and height. And you see why we talked about all this base and height and so forth, right? And also, you're going to need those three postulates. The area of a square, the area congruence postulate, and area addition postulate to actually prove this theorem. The area of a rectangle equals the product of its base and height. And in short, A equals to B times H. Okay. Now, to prove this, you're going to need some hints. Okay, so take a look at, here's our picture. In order to prove this, we're going to draw a bunch of auxiliary lines. And the way to do that, you see how I have the base times H, this blue area? That's the rectangle, right? Area of the rectangle. Now, what I'm going to do is I'm going to extend H amount, which is the same as the height, towards where the B is, and I'm going to extend the height same as the length of the base over here. By the way, what is this whole then length of this big B plus H? What about this one right here? What is this whole thing? It's a square, isn't it? Because, right, this is the length of this is B plus H, right? This, right? Base is B plus H also. Okay, so, and don't we know how to find the area of a square? Okay, so knowing this then, and they drew auxiliary lines like this, how can we show that this area, this blue area, is equal to B times H? Knowing what we know, the area of a square, the area congruence postulate, and area addition postulate. Some of you already. I want you to think as a group. Go ahead. I'll wait. How would you do this? Think about it. Okay, so I'm gonna give you a hint. Let me ask something here. By the way, I'm gonna call it this whole area of the big square as ABS. Is that okay? Because I don't want to keep writing that. Anyway, if this rectangle that we're looking for, the area is A, what's the area of the one right here?
Where?
This one right here.
Where?
Oh, sorry. You can't see. Sorry.
No, it's not.
This one.
Oh.
What's that area? It's also A. Why? Because they are congruent. Remember we talked about if two figures are congruent, what do you know about their area? Yeah, this is H by B. This is also H by B. Isn't that right?
Yeah.
Okay, that's a hint. And do you want one more hint?
Yeah.
There are two ways to represent the area of this big square. There are two ways. Think about how to do that. Then it should make sense. Go ahead, I'll wait for you. Go ahead, everybody think. All right, so I think a lot of you guys already got this. Okay, so somebody tell me, what did your group come up with? How about Michael? What did your group come up with? What's one of the way of representing this ABS, area of the big circle? I mean not circle, square. Say what? If you do, you get two triangles. We haven't learned, even though we know how to find the area of a triangle, we haven't learned or proved it, so you can't use the area of a triangle. Okay. So what's, Michael, let me ask you, if this area right here is A, right here, right? And if this area is A, what's the area of this square right here? This one right here. H squared, isn't that right? That's H squared. What's this area of this B by B, this square? Isn't that a square also? Using the postulate, what is the area of this square? B squared. Don't you have two of these squares, right? Yeah, add it all together. What do you get? H squared plus B squared plus
2A.
A plus A, which is 2A, right? Question? Does this make sense?
Yeah.
All right. What's the second way of representing the area of the big square? How about, what did your group come up with? How about Austin? What did your group come up with?
It can also be 2 times b times 8.
That's what I have right now.
Yeah.
No, Austin.
2bh.
No, the second one is h squared.
Okay, so that's not correct.
What's the question?
The question here. First of all, Austin, do you understand where I got h squared plus b squared plus 2a? You got that? Now, there's another way of representing the area of this big square. Is there? How do I do this?
Oh, b plus h squared.
Yes, because this whole length right here is b plus h, right? What about this one, class?
B plus h.
And we know, we just said this is a big square, right? So b plus h times b plus h, right? Which is b plus h squared. By the way, do we know how to multiply this? From algebra, we know this is b squared plus what? 2bh plus h squared. Okay, now, if that's true, if both of these represent the area of this big square, well, using substitution property, this would equal to what? This. Okay, let me write it down using substitution. H squared plus b squared plus 2a equals to b squared plus 2bh plus h squared. By the way, using the subtraction property of equality, what can we do with these? What else can I cancel out?
B squared.
Okay, so what are you? Okay, good. Hold on. So what's left now? And what's a? So that's the reason why. Okay. So do you see how? Okay. Do you see how the area of a rectangle comes from using the area of a square and these two postulates that we learned? Any question? Does this make sense? Yes. Good. It's pretty straightforward. Let's do some examples then. Okay, here we go. Our first example says this. Find the area of a rectangle whose base is 3.5 centimeters and whose height is 2 centimeters. This is pretty straightforward. Who can tell me what this is? Chris, what'd you get? You got it. 7 centimeters squared. Would you not agree? Can I say 7 centimeters? Okay, that would be wrong, right? Okay. Second, a question is this. Now this time, I give you this figure. I want you to find the area of this yellow region. Now, notice it doesn't give you any sort of unit. So what are you going to use as your unit? Just unit, okay? You got to use unit. All right, go ahead. Everybody try. There are 2 ways of figuring this out. I'll wait for you. Go ahead. Everybody try. All right, who could tell me one of the way of getting the area of this rectangle? I mean, not a rectangle. This figure. How about Andrew? What can you do?
What? Oh, you can do 8 times 5, which is 40, and then that little square is, what is it? It's a square, so, what is it? 2 times 2 equals, 2 times 2 equals 4, and then 8 times 5 equals 40, and 40 minus 4 equals 36.
Good. So you could do it that way. Very good. Now, how did you know that this was a square? Who could answer that question? How about, hold on, how about Tony?
The 8 is right. So the top with the red line, that's the rectangle. So
Mhm.
the bottom is 8 also. And then we're given, we could use the same for the bottom one. So 8 minus 6 equals 2.
Exactly. So you got top, this whole thing is 8, the whole thing, and this is 6, so it's got to be 2, right? All right, that's pretty simple. What's another way of doing this? How about Josh?
I just said Tony's way.
Think about the other way. Let me give you a hint. Look at the red dotted line. Look at the red dotted line here, Josh. Josh, let me give you a hint. Another hint. Area addition postulate. Josh, do you remember area addition postulate?
Yes.
What would happen if I were to cut this right here? And wouldn't you get a rectangle on top and another smaller rectangle on the bottom?
Yes.
Can't you add those together?
Yeah.
Okay, so what would that area of the top rectangle be?
So that's 12 plus 12 plus 24.
Exactly, because this whole thing is 5. Right here, this is 2. This got to be 3. So 8 by 3, isn't that right? That's what you have on the top rectangle. And you have 2 by 6. Yes? And so you get 36 both ways. Any question? Easy enough. Can you do something like this for your homework tonight?
Yeah.
Okay, good.